So now let's talk about multinomial coefficients. I always think of multinomial coefficients as a destiny assigning number. So let's see why. Suppose we have 3 dragons that kidnapped 3 princesses. Each dragon kidnapped a princess, and there are 10 brave knights that will be sent to rescue them. So 3 of the knights will be sent to fight dragon number 1. Another 3 will be sent to fight dragon number 2. And the last 4 will be sent to fight dragon number 3. He looks like he has eaten quite enough knights. So, how many ways are there to assign the knights their destinies? Well, I can look at the knights and list them in order. So we have knights, let's say, knights 1 to all the way to knight number 10. And I list the knights in order, and what I have here is a tray. So let's say that the first tray contains 3 individuals, because that's going to be food for dragon number 1. And that requires 3 knights. The second tray will contain another 3 individuals, and they will go as food to dragon number 2. And the last tray will contain 4 individual knights, and that tray will go to dragon number 3. So let's see what happens here. So I will arrange the knights in linear order. Since there are 10 knights, you can see they're going to be 10 factorial linear orderings. But clearly the knights that end up in tray number 1, containing 3 individuals, that's tray number 1. Their destiny is to be going to dragon 1. This is tray number 2, as I said, right? To go to dragon number 2, and tray number 3 to go to feed dragon number 3. So there are 10 factorial ways of arranging the knights in a row. And then for each arrangement, you see that if I permute the knights that ended up being in tray number 1, it's not changing their destiny. They're still in tray number 1. If I permute the knights in tray number 2, doesn't change their destiny. And so there are many codes, right? The 10 factorial codes, but a bunch of them correspond to exactly the same outcome. How many? Well, I can divide here by 3 factorial, and another 3 factorial, and a 4 factorial. So this would be 3 factorial, 3 factorial, and 4 factorial. So this is the multinomial coefficient written as 10, and we have choose 3, 3, and 4. Notice that those numbers have to add up to 10. Right? So what is it in general? In general, if we have our dragons and n knights, such that and one of those knights go to dragon number 1, and 2 of those knights go to dragon number 2, and R go to dragon number R, where of course N1 plus N2, they have to add up to N. If that's the situation, then how many destinies are possible? Well, I have N knights, so I have N factorial ways of placing them of placing the knights in linear order. How many trays do we have? Well, we have R trays, where each tray is a dish for the dragon. So that would be that's requiring N1 individuals to go to dragon 1. And then we have a bunch of other individuals, that's for dragon number 2, and onwards until we get the tray containing the knights that go to dragon number R. So there are n factorial ways of placing the knights on those trays, with each tray representing a different destiny. Now, if I permute the knights that land in tray number 1 among themselves, that does not change their destiny. If I do the same for tray number 2, that again does not change their destiny. So you can see that then a bunch of orderings correspond to the same destiny, and for each destiny, how many orderings are there? For each destiny, there are n1 factorial orderings here, and 2 factorial orderings there, all the way until we get to nr factorial orderings. So this is then the coefficient n, choose n1, n2, nr, also known as a multinomial coefficient, as will be explained shortly. So why is this expression called a multinomial coefficient? Let's try to see how this expression helps us expand a multinomial product, right? So you have a bunch of variables x1 through xm, and we raise the sum of the variables to the power of n. How will we accomplish that? Well, we can now break it into several parentheses. So first parenthesis indicated by this number 1 over here. Second parenthesis indicated by this number 2. All the way until we get to the end parenthesis, here indicated by the number n. So when I expand this product, I see that I am adding numbers, well, I'm adding terms where each term is a product of n variables. This is 1 means how many variables of type x1 do we get, x2, do we get a variable from the second parenthesis, so this means, this box means how many variables we get from first parenthesis, and this is how many variables we get, variable we get from the second parenthesis and onwards. In other words, this is what this first box means. This is either x1 or x2 or x3, etc. It's one of those variables will be selected as a delegate from first parenthesis. In the second parenthesis, we will select, again, they are the same delegates, I just indicate by the second subscript that they come from the second parenthesis. Which delegate comes in here? So either x1 or x2 or x3 and onwards, right? So it's always going to be a product of n delegates, where each delegate is either x1, x2, etc. And this is just a representative from first parenthesis. This is a representative from second parenthesis, etc. So the summation, if you think about it, will always look like this. I can break it based on the different powers that each x can have. So let's suppose that, well, I want to group together all terms where x1 is raised to the power of n1, x2 is raised to the power of n2, and xm is raised to the power of n sub m. That means the summation will go over all possible vectors, n1, n2, all the way to nm, where the sum n1 plus n2, all the way plus nm, equals to n, the power. So I need to just figure out what coefficient goes in here. So in this question, who are the knights and who is the dragon? So how many knights do we have? So the power here, the power n, those are the knights. So we have n knights. And for a particular vector, that indicates what? So the variables are the dragons. How many knights will go to x1, to the first dragon? How many knights go to x2, the second dragon, and onwards? Okay? So those are the knights they will claim. Now that is now easy to answer. So the destiny of n1 knights is to be food for dragon 1, of n2 knights to be food for dragon 2, etc. So the coefficient here is n, and then we have n1 knights will go to x1, and 2 knights will go to x2, all the way to n sub n knights, which will go to this variable. That is the coefficient of the multinomial variable. It's a bit more complex than with the binomial theorem, but I hope you follow this reasoning. So let's finish it with one final problem. Suppose we have 9 pupils, and the 9 pupils will be divided into 3 teams, each consisting of 3 players. There is going to be one team wearing a red jersey, another team wearing a blue jersey, and one wearing a green jersey. How many possible team arrangements are possible? So what we have is, we can label the pupils as pupil 1, pupil 2, all the way to pupil 9. And then we are going to construct a document that will represent jersey assignments, right? So this will contain red team. This will contain blue team, and the last will contain the last box will contain the green team. So this is my document. So for example, if I fill in the document and I write child 1, 2, and 3 were assigned to the red team, 4, 5, 6 assigned to the blue team, and 7, 8, 9 to the green team. Let's suppose that in this document we make the stipulation that I always present the team members in order from smallest to largest. So for example, I could not see 3 to 1 or 3, 1, 2. It has to be in increasing order. Okay? So what happened here? This red group is the dragon red. It will be assigned children 1 through 3. Dragon blue is assigned children 4 through 6. So their destiny is blue, and the destiny of 7 through 8 is green. So you can see that we have then the children are the same as the knights in the previous question. So we have 9, choose 3 numbers to go in here, 3 numbers to go in here, and 3 numbers to go in there. This is nothing more than just to calculate 9 factorial divided by 3 factorial, 3 factorial, 3 factorial, or if you prefer, simply 9 factorial divided by 3 factorial cubed. Now let's make this question slightly more difficult. Now suppose in B, only the red shirts arrived. We are going to divide children into still into 3 teams, but only the red team is assigned a red shirt. What happens then? Now you see there is the code 1, 2, 3, 4, 5, 6, 7, 8, 9. So I write this code again here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And I no longer, in question B, I no longer have a blue team or a green team, which means that those no longer are different destinies. Being together on the team is a different destiny, but not this, right? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Used to mean that this is a blue team and this is the green team. But now I have another code, so I have 1, 2, 3, and I can write 7, 8, 9, 4, 5, 6. Now this code and that are no longer corresponding to different outcomes. It's just, it could be the blue team, it could be the red team, we don't know, right? We just have those teams. So now the solution is that now those codes are overcounting. This is now an overcounting. By how much? Well, clearly exactly by 2, right? So the solution would have been very simply 9, choose 3, choose 3, choose 3, divided by 2. So for each unique outcome, now you have 2 codes, because we cannot tell which is the blue team and which is the red, the green team. Only the red team is distinguishable. Now let's try to see what happens if C, no shirts arrived. What now? Well, no shirts arrived means we now no longer have red. How many possibilities are there now? How many destinies? What is a destiny in this case? The destiny can only be determined by the teammates, right? So here 1, 2, and 3 are together, 4, 5, and 6 are together, 7, 8, 9 are together, but I no longer know which team is assigned to which shirt. So this is now overcounting by how much? So we have 9, choose 3, choose 3, choose 3. You can see that every code I can permute it, right? I can interchange any of the boxes among themselves, and that will be 3 factorial interchanges. That means that we overcount each destiny using this code scheme exactly 3 factorial times, which means our solution is 9, choose 3, choose 3, choose 3, divided by 3 factorial. Or if you prefer, it's 9 factorial divided by 3 factorial to the power of 4. Well, hopefully that was understandable enough, and let's move on.